All right, welcome everybody to the MCube Weekly Seminar. Today we're honored to have Craig Schwartz. Craig got his BS in Meteorology from Penn State, MS in Meteorology from Oklahoma, and PhD just recently, last year, in Atmospheric Sciences and Oceanic Sciences from University of Maryland. Since 2009, he's been here at MCubed. Craig has extensive experience and expertise in the areas of forecast verification, data assimilation, ensemble forecasting, with particular emphasis on high-resolution modeling systems. He was actively involved with the popular NCAR Ensemble project that produced real-time, high-resolution ensemble forecasts from between 2015 and 2017. Craig has co-authored over 50 articles in peer-reviewed atmospheric science journals, and if that wasn't enough, he's editor-in-chief, associate editor-in-chief for Advances in Atmospheric Sciences, and associate editor for both Monthly Weather Review and for Weather and Forecasting. And those of you who remember our pre-COVID holiday parties, remember that Craig is an excellent pianist, and I hope to hear him again someday. All right, cheers.
Thanks, Rich. All right, hi everyone. So this talk is unabashedly applied. It's about weather forecasting, but I think it definitely has some important implications for how to design kind of next generation regional numerical weather prediction systems, particularly ensembles. So before going too far, I just want to acknowledge that a lot of folks contributed to this work, some individuals that left, but really, all of MCube and all the WRF developments, this work would not be possible without all of that. Also folks in CISL who maintain the DART software. So just a brief acknowledgement to all the many folks who in some ways were at least indirectly involved in these experiments. So when it comes to weather forecasting, the state of the science is what is called a convection-allowing model. And this nomenclature, convection-allowing, means that we're going to remove the deep cumulus parameterization scheme such that convection can organically form through the model dynamics. And you can typically do this when the grid spacing becomes sufficiently fine. Now, the definition of sufficiently fine depends on a bunch of things, and one thing it does depend on is the geography. But over the United States, typically, once we get to about 3 or 4 kilometer horizontal grid spacing, we can remove the deep cumulus scheme and allow convection to organically develop. In short, these models are amazing. They've revolutionized weather and forecasting. NCAR actually had a huge role in making these popular back during the BAMX field campaign. That was really the first time a real-time convection-allowing model had been run. And ever since then, it's kind of been a one-way ticket towards convection-allowing modeling. And as computing has continued to advance over the past 20 years or so, operational center after operational center after operational center around the world had just moved towards convection-allowing models. For those of you who haven't spent much time looking at what this output looks like, here's just a simulated radar image from a convection-allowing model. One of the things you really get from them is just detail that looks a lot like what you would actually see in nature. For instance, we have predictions of individual supercell thunderstorms here that we can get from these convection-allowing models that you probably cannot get with coarser resolution models that have a deep cumulus parameterization scheme. But we all know that models aren't always accurate, and so one individual forecast is of questionable value, and so really the frontier is what's called convection-allowing ensembles. And so in a convection-allowing ensemble, we have multiple realizations of a forecast model valid at the same time. So you can see a variety of solutions. So this is what's called a postage stamp plot, where we have 10 ensemble members. This is the reflectivity, and you can look at the different members and see that they look different in certain places, or they might look more similar in certain places. And so while it's fun to look at these and you can get some valuable information, the real point of ensembles is to take this sort of information from our individual ensemble members and to synthesize them into probabilistic fields. Probabilistic guidance is really the main motivator for ensemble forecasting. So what's shown here is just the probability of reflectivity greater than 40 dBz within 25 miles of a point. And we can see areas over Oklahoma where the ensemble is pretty confident that there's going to be convection, and then some areas over southeastern Missouri where it's not as confident that there's going to be convection. So these really are the frontier of regional weather modeling and high impact weather forecasting. But there still are a lot of questions about how to develop and improve these convection-allowing ensembles. So one thing you can do is you can improve boundary condition perturbations. This can be important, especially if your domain is relatively small. Stochastic physics techniques, it's a really hot topic right now. Improving these can lead to better spread characteristics of an ensemble. Multiphysics configurations, they're still used. I put a question mark. I think a lot of folks would like to see multiphysics configurations be abolished and kind of move towards stochastic physics approaches with a single physics technique, but these are still used, they are still popular, and there probably are ways to improve them should one feel inclined to try to do so. And then what this talk is about is improving the initial conditions. And if we're going to be talking about initial conditions, that means we're talking about data assimilation, and in particular, I'm going to be focusing on the ensemble Kalman filter. And it's well known now that initial conditions play a large role in the quality of convection-allowing ensemble forecasts, particularly over the short term, but if your domain is large enough, they can play a big enough role through, say, 48 hours even. So the research questions that I'm going to look at are, one, what is the best cycling strategy for data assimilation systems? And I'll describe what this means, and I'll talk about partial versus continuous cycling in a data assimilation system. And then also, are convection-allowing ensemble forecasts sensitive to the resolution of the initial conditions? So these are really fundamental questions about convection-allowing ensemble initial conditions that we don't fully know the answer to, but they're really timely questions, especially given what NOAA is doing right now in terms of trying to develop the rapid refresh forecast system. This is a model that's supposedly going to become operational sometime, I think, in late 2023. It is going to basically replace all of the regional models that you know and love, like the RAP and the NAM and the SREF and the HER and the NAM-NEST and the HREF, the current high-resolution ensemble over the United States that really isn't a formal ensemble. It's just a collection of deterministic forecasts all mashed together. So there are some serious questions about how should this new system be initialized, and what data assimilation strategies and configurations should we consider in this new model. So first I'll talk about cycling strategy, partial and continuous cycling, which means I have to talk about data assimilation, which is enough to give most folks heart palpitations. Yeah, data assimilation is complicated and hard. But for the purpose of this talk, you don't need to really worry about the complicated and hard details. In a nutshell, here's what we do. We start with a gridded model forecast. This is typically called a background. Sometimes it's called a first guess in some situations. Sometimes it's called a prior. So I'm probably going to use the term prior and background a lot when talking about this. But the idea is we have some field, it's on your model grid, and you think it's a good guess of what the true atmospheric state is. Then we have real observations, like a thermometer that I could be holding. And the idea is to take these real observations and update this model background. So we're going to combine observations and the model background in the data assimilation system. But it's not quite that simple because observations aren't perfect. There are errors. And we certainly know that a gridded model forecast isn't perfect. And so the observation errors are the errors associated with the observations. And then we have this term called the background error covariances, which are associated with the background. You often hear these abbreviated as just BECs, or background error covariances, and data assimilation folks love to talk about background error covariances, and some scientists will devote their entire career to just the background error covariances. This is a really important part of data assimilation. And when you hear about 3D VAR or an EnKF or a hybrid or an EnVAR or a particle filter, all these various data assimilation forms, the primary difference is the background error covariances. There could also be some differences in the observation errors and how those are specified, but the main difference across these various DA systems is the background error covariances. So we have our background and observations, and then error characteristics of both of them. And then we combine them in the black box, our data assimilation system, and it spits out for us a gridded analysis. And this analysis basically is the initial conditions that you would then use to run your forecast model. This is all I'm going to say about data assimilation. One reason why the ensemble Kalman filter is really popular is because of how it treats these background error covariances. In everything that I'm going to talk about, this is the procedure that's going to be happening basically over and over and over. In this case, every hour, we're going to basically be doing this sort of procedure where we combine these 4 elements into an ensemble Kalman filter. The only difference is we have an ensemble of background states, and we're going to get out an ensemble of analyses, or an ensemble of initial conditions. And it's through the ensemble itself that you get these background error covariances. So for an EnKF, you can just think of the background error covariances to first order simply being the ensemble spread. So I think a lot of folks, when they're introduced to data assimilation, the first thing they're shown is this horrible cost function for 3D var. And 3D var is a lot harder because of how it deals with the background error covariances. You can just think of the background error covariances again as the ensemble spread. And that's really kind of how the EnKF works. So now that I've given this brief overview of DA, I can try to introduce these cycling strategies. So there are 2 overarching strategies that we can use in a regional data assimilation system: continuous cycling and partial cycling. So for continuous cycling, we need to kick things off. This is a regional model that we're talking about. So we've got to kick off something on our limited area grid. The way we do this is we take an external analysis or a forecast. It's usually derived from global fields. We can also just add random noise to a single deterministic field. And actually, for continuous cycling, it doesn't really matter too much how we kick things off, for reasons that hopefully will become a little bit clearer. So for the first cycle, we kick things off. We have an ensemble of our background states at our very first cycle. And then thereafter, we have this period of self-contained cycles, where we combine this background of ensemble members with observations into the EnKF. The EnKF spits out an analysis ensemble for all of the ensemble members. And then this entire ensemble is used to initialize a short-term model forecast that then becomes the background for the next data assimilation cycle, where we again combine the background with observations into the EnKF. And we can just do this over and over and over and over and over. This is how global models work. Global models, you don't really have 2 options. You have to continuously cycle. And what this does is when you do it with a regional model, is it yields a self-contained data assimilation system where we don't have any influence of global models at all, except for boundary conditions. And if you make your domain big enough, really the impact of the boundary conditions on the system are going to be pretty small. So again, aside from kicking off the EnKF with the external fields, we always cycle. And because we're always cycling, eventually the model's going to adjust toward these observations, and it's going to completely forget about how it was kind of kicked off at the very first cycle. And so that's why I say it doesn't really matter how you initialize this continuously cycling system. So we can do this EnKF cycling over and over for however long we want, and then when we feel like it, we can take some of our analysis members and then use them to initialize a free forecast unconstrained by data assimilation, like a 36-hour forecast or something like that. So that's continuous cycling. Now here's partial cycling. Again, at our very first cycle, we've got to kick things off with some external information. But in partial cycling, now it's going to matter what we do. It's going to matter a lot, potentially. So again, first cycle, we kick things off with some external analysis or forecast. We get our initial background ensemble. And then just like continuous cycling, we then have this period of self-contained cycles where we combine the background with observations in the EnKF. It gives us an analysis ensemble that then initializes a short-term ensemble of model forecasts that become the background for the next cycle. And so we do this for some period of time. But then we get to our last cycle, which is typically a forecast initialization time that we're interested in. And at that point, then we break the cycle. We no longer use our analysis to initialize a short-term forecast that becomes the background for the next cycle. And instead, we just initialize a free forecast, and then we're done. And so the next day, we start all over again. And so here's the whole cycle, where we initialize from our external analysis or forecast to kick things off, make our initial background. We do a period of cycling until our time of interest. And then at the time of interest, we can run a free forecast, and we break this cycle. And so because of the fact that we're bringing in this external information, really however often we choose, between 6 and 24 hours is common, this can matter a lot in a partial cycling system, how you are initializing your regional model in this data assimilation framework. So there are some major challenges with partial cycling. For instance, forecasts are possibly sensitive to how often we ingest this external information that is typically provided by a global model. Additionally, the forecast could be sensitive to characteristics of these external fields, like bias characteristics of a global model, or the spread if you're dealing in an ensemble framework. In terms of workflows, they can be a tremendous, tremendous pain. Sometimes you actually have to run 2 limited area systems in order to complete a partial cycling system. Perhaps the biggest problem, though, is that they can hide limited area model errors, so it's harder to fix them. Because you're starting things off with this global model, in some ways, your system is going to be tied to what you're bringing in. And so if there's a problem with your model, what's the cause? Is it due to the global model being bad, or is it due to your regional model being bad? In many ways, there's no way to really disentangle those, and I've seen instances where bugs have been found. And for instance, certain observations just weren't assimilated, and folks never knew because having this global model start things off just kind of hid the problem. So from a model development perspective, partial cycling is not good. Conversely, continuously cycling data assimilation systems are easier to maintain, they can have simpler workflows, they have fewer sources of sensitivity, you only have to really deal with one model, just your regional model, and through the cycling, you can expose model errors. You can really see the biases and if they grow, and in theory, if you know there are model errors, then you can theoretically fix them. So given these pretty clear benefits of continuous cycling, you'd think it would just be a no-brainer that that's what you would use in operations. Well, there's one small problem with that, and that is that partial cycling has historically done a lot better than continuous cycling. So about 10 years ago, or even more now, studies indicated that partial cycling systems initialize better forecasts than continuously cycling systems over the United States. Similar results were also found over Taiwan and some other countries as well. And so currently, today, NCEP is using partial cycling for all of its regional models in some flavor. The NAM, the RAP, the HER, in some flavor, they're all using this partially cycled system. But these studies 10 years ago were using an older data assimilation technique called 3D VAR, and we have better techniques nowadays, like the Ensemble Kalman filter. And so I think it's time to revisit this topic of partial versus continuous cycling over the US with a modern data assimilation system like the EnKF. What we're going to ask is, can a continuously cycling system initialize comparable quality convection-allowing ensemble forecasts as a partial cycling system? And relatedly, what should this new rapid refresh forecast system use? So to set about answering these questions, we designed 3 EnKF experiments. They were all identical except for the cycling strategy. One of the ensembles was an 80-member EnKF, and it was continuously cycled. The other 2 were these partial cycling systems. Again, they both had 80 members. One of the partial cycling systems was initialized at 6 UTC each day, and it performed 18 hours of self-contained cycles until 0 UTC. And the other partial cycling system was initialized at 12 UTC each day and performed 12 hours of self-contained cycles until 0 UTC. All these had 1-hour data assimilation cycles. We had a 4-week period, and at 0Z, that was our forecast time of interest. So that's when we launched these 36-hour, 3-kilometer, 10-member convection-allowing ensemble forecasts that really are of most interest here. Here's a computational domain, CONUS plus. It's a big domain, so boundary conditions are applied way out here in the Pacific, so boundary conditions weren't really a huge factor, at least in the data assimilation system itself. As for the model and DA systems, we used WRF, version 3.9.1.1, 51 vertical levels, 15 millibar top. A well-tested physics suite, it's basically the CONUS suite that was implemented in WRF. For the DA, we used the EnKF from NCAR's DART software for the actual filter algorithm itself. But for observations, we used NCEP's operational GSI data assimilation system that we hooked up with DART. And the reason for this is simply because DART is an excellent tool. I really, really like it, but it was not really designed for major observation processing. GSI, on the other hand, NCEP's operational thing, they've been working on that for decades. So there's a lot of potential benefits to using observation quality control kind of coming through that system. So that's what we did. There are a ton of technical details here that I'm just simply not going to go into. So if you want them, you can ask, or you can see the paper. In terms of the observations that we assimilated, were pretty well observed over the United States. We simulated radiosonde, aircraft, satellite-tracked wind AMVs, surface observations, wind profilers, GPS-RO. We did not assimilate radiance observations. If I were to do this again, I would. I don't really think it had a huge impact on the results, but we can talk about that. So just to kind of reinforce this experimental design for the continuously cycling system, we have our 15-kilometer background of 80 members, gets combined with OBS into our 15-kilometer EnKF, produces a 15-kilometer analysis ensemble that initializes 1 hour WRF model forecasts. Then we cycle for a period, and then at 0 UTC each day, we initialize 10-member, 3-kilometer ensemble forecasts. And because we were only performing 15-kilometer data assimilation, to initialize the 3-kilometer forecast, we have to downscale the 15-kilometer analyses onto the 3-kilometer grid. For partial cycling, we got to kick things off. So at our very first cycle at 6 or 12 UTC, we kick things off, and the way we did that is we basically used NCEP's global ensemble. That's the easiest way of thinking about what it was. NCEP's global ensemble is kicking things off. It's providing the background at either 6 or 12 UTC, and then thereafter, we do a period of self-contained cycles, just like in the continuously cycling EnKF, and then when we get to 0 UTC, we again initialize 10-member, 3-kilometer ensemble forecasts with these downscaled initial conditions, and then we start over again the next day. So here's the whole flow chart for the partial cycling, where each day we're bringing in this global ensemble. And so the real difference between the partial and continuous cycling system is this. It's this external information that we're bringing in. We're kind of looking at the forecast sensitivity to what happens when you bring in this global information periodically, as opposed to just letting the WRF model cycle on its own for a 4-week period. When we ran the 3-kilometer forecast, here's the domain. So our analysis domain is this 15-kilometer domain, and then we plop the 3-kilometer nest in there that covered the entire conterminous United States. And just to reiterate, these 3-kilometer initial conditions are these downscaled 15-kilometer analyses. So one thing that we were particularly interested in was how the 0 UTC partial and continuously cycling EnKF states differed. In other words, if we look at 0 UTC, what do these states look like? Because we should see some differences, because one of them has brought in global information fairly recently, and the other doesn't know anything about this external global information. What we're going to try to do is attempt to link forecast differences to differences in these 0 UTC initial condition characteristics. We looked at a bunch of things, but what I'm going to show you here is a spectral plot. What's shown here are spectra of differences between the EnKF mean analyses and GFS analyses over all 26 of our 0 UTC analyses for 850 millibar temperature and mixing ratio. So we have wavelength on the x-axis in both of these panels with small scales to the right, large scales to the left, and the y-axis is a difference energy. So it's a difference. So smaller values mean that the EnKF looks more similar to the GFS. Larger values mean that there are more differences compared to the GFS. So if we're looking at relatively small scales for both 850 millibar temperature and 850 millibar mixing ratio, we don't see a lot of differences. But once we get to about 1,000 kilometers and greater, that's where we see some differences. So this purple curve is for the continuously cycling EnKF, and the green and orange are for the partial cycling EnKFs. And for both fields, we can see that the difference energy is greater in the continuously cycling EnKF, which means that the continuously cycling EnKF looks more different than the GFS analysis than the partial cycling EnKFs, which are shown in these orange and green lines. I think this makes sense because in the partial cycling EnKF, we are kicking things off with effectively what is a GFS field. What this is showing is that after 12 or 18 hours of cycling, these partial cycling EnKFs still have some memory of the larger scale fields from the GFS. And these larger scale fields we're going to see are going to be really important when it comes to forecast quality and the differences between the continuously cycling EnKF and the partial cycling EnKFs. So turning to precipitation verification, we're going to focus on 1 hour accumulated precipitation from the 3-kilometer forecasts over the CONUS east of the Rockies, over this large verification domain. NCEP stage 4 observations are our truth. I'm going to focus on aggregate statistics over 26 forecasts using a technique that uses percentile thresholds. This controls for bias. In other words, instead of verifying, let's say, precipitation exceeding 10 millimeters an hour, now we're going to verify, say, the top 5% of both forecast and observed events. This removes bias completely. And I was really interested in the spatial placement. Is it raining in the right place at the right time? And I can evaluate bias separately. I don't want bias to contaminate these measures of spatial displacement. So that's really the power of using a percentile threshold technique. We'll use bootstrapping, but I'm not going to show it because it makes the figures look a little bit too ugly, but I'll try to tell you when differences are statistically significant. And we use a neighborhood approach for the verification. The way this works is we take a central grid point of interest, and we define a neighborhood about this point, here denoted by R, which traces out a circular neighborhood about our central point of interest. And then we define an event, like the top 5% of precipitation accumulation values, and those are in these gray shaded boxes. So note that at this central point of interest, we don't have an event. But if we look within the neighborhood of our central point, the event actually occurs 8 times. And so we can say at this point, we basically have an 8/21 or 38% chance of the event occurring, because the event occurs 8 times within the neighborhood, and there's 21 grid boxes within the neighborhood of this point. So this is what you do for a deterministic forecast, and then since we're dealing with ensembles, what we do is we apply this exact same approach separately to all 10 of the individual ensemble members. We generate 10 probabilistic fields by this neighborhood approach, and then we average it. And back in 2010, we called this a neighborhood ensemble probability. And this is what we'll be verifying. I'm mostly going to focus on the fraction skill score, which is where we compare forecast and observed fractions. And yes, observed fractions. We also apply this neighborhood approach to the observation field as well. So in this equation, both f and I are fractions. They both vary between 0 and 1 is perfect. And this fi fractions, these are our neighborhood ensemble probabilities. We looked at a lot of different metrics. I'm just going to focus on the fraction skill score, but focusing on other metrics really tells the same story. So on to the results. First, I should say the tie here goes to continuous cycling. I say in baseball the tie goes to the runner, but here the tie goes to continuous cycling. Because of the many benefits of continuous cycling, really, it just needs to be as good as partial cycling to potentially justify an operational implementation of a partial cycling system. So here we have the fraction skill scores on the y-axis. Forecast time is on the x-axis. And these panels are for different precipitation percentiles. So this is the top 5% of events, the top 2.5% of events, and the top 1% of events. In purple, we have the continuously cycling EnKF, and in green and orange, the partial cycling EnKFs. So if we focus over the first 18 hours or so, and we look at this purple curve, that's for continuous cycling. And we see that its fraction skill scores are either higher than or roughly the same as the partial cycling EnKFs over the first 18 hours. In other words, over the first 18 hours, partial cycling cannot beat continuous cycling. But when we look after 24 hours, then we kind of see a different behavior. But pretty clearly, the partial cycling systems shown here in this green and orange, these are giving us higher fraction skill scores than our continuously cycling EnKF, and these differences are statistically significant at least the 95% level. And so this is kind of interesting. We hypothesized that this was due to aspects of the large-scale initial conditions, because the large scales should become more important as forecast length progresses. And so we tested this hypothesis by doing a blending approach. Now, this isn't as exciting as like blending, in this case, what are these called? Glow tubes or something like that? So we're not blending those. Instead, we are blending fields from 2 different models. So what we did is we blended the large scales from the global ensemble run by NCEP with the small scales from the continuously cycling EnKF, and kind of made this hybrid or blended set of initial conditions that at small scales looked like the EnKF, but at large scales looked like a global system. There are lots of ways you can do this blending. We use a tangent filter. You have to specify kind of a wavelength where you transition between large and small scales. We tested a few different of these cutoff parameters, and there wasn't a ton of sensitivity. So in this case, we use a 960 kilometer cutoff. So at 960 kilometer waves, half of the contribution is from the regional EnKF, and half of it is from the global ensemble. So we implemented this blending approach within our continuously cycling EnKF. So here's the continuously cycling EnKF. The important thing to note is we blend after we do the analysis, but we don't allow the blending to impact the data assimilation system itself. We're just blending immediately before initializing our free forecasts. And this was done to just kind of preserve the integrity of the continuously cycling data assimilation system. There's no reason you can't incorporate blending within the cycles themselves, though, if you wanted to do that, but then you're kind of destroying the whole point of continuous cycling to a certain extent. So here's what I showed before with the fraction skill scores on the y-axis and forecast time on x. And now the black curve is for the blended initial conditions. And I'll just go back and forth a couple of times. So over the first 18 hours or so, these blended initial conditions lead to fraction skill scores that are just as good, sometimes even better, than the continuously cycling EnKF. So blending is not messing things up over the first 18 hours. That's important. But then, at later times, 24 to 36-hour forecasts, if we compare the purple curve and the black curve, we can see that we get a performance boost now from blending that kind of gets us closer to where the partial cycling systems are. So blending is a way that we can incorporate it into a continuously cycling system, allow the continuous cycling to occur within the DA system itself to kind of get the benefits of identifying biases, but then get a performance boost at later times. So the takeaways from this are partial and continuously cycling EnKFs. They led to comparable quality forecasts through about 18 hours, but after 18-hour forecasts, partial cycling led to better forecasts. We can blend, combine that with continuous cycling, and that gives 18 to 36-hour forecasts that are as good as those initialized from partial cycling analyses. I would argue NCEP should seriously consider something like this, and they are aware of this work, and they are considering something like this. We'll see what they end up actually doing for their system. This is a good time to pause and take questions on this. I've got another 10 or 15 minutes after this, kind of part 2, but this is a good natural starting point, and if you want the gory details, read the paper.
Yeah, so this is an intermission with questions. So anyone have any questions or comments?
Hi, Craig. Yeah, really great seminar. How much do the results depend on the physics? I mean, what makes the need for partial cycling is that results can start deviating from nature or real climate. So have you tried to do this with more than one physics suite, or what NCEP's going to run a different physics. How is that going to work?
Yeah, that's a good question. In short, we haven't looked at it explicitly, but we have done work where we continuously cycled systems with like the RAP physics suite. Didn't go very well. Something that I neglected to say earlier is one of the reasons why continuously cycling worked kind of as well as it did here was because of the physics suite that we were using, which we had looked at in sensitivity studies like 10 years ago. And we've been using the same physics suite for a long time. So we know that it behaves pretty well and leads to fairly unbiased priors. So that is one reason why it probably did work, is because we think this is a pretty good physics suite, at least over the United States, for this sorts of application.
Yeah, Craig, you might have said this already, and I tuned out for like 1 second, and I probably missed it. For the continuous cycling, could you do something as you're leading into what would be a partial cycling, start, do nudging, like the, spectral kind of approach to bring in the large scale in a more gradual way to sort of, I just wondered if that's being considered.
I mean, you probably could. Certainly spectral nudging is another way to kind of bring in large scale stuff. And there are other ways of bringing in large-scale information as well. This isn't the only way using this filter. You can actually do like data assimilation where you assimilate pseudo-obs like from, say, ECMWF, for instance, into your DA system. You can do variational things where you have a whole other term for a large-scale constraint. So there are definitely other ways. We didn't look at them in this work.
So if you would use a global model with a regional refined domain, would this place here? Would this be similar to blending? Would it be better, or?
I don't know. The whole question about global is intriguing when it comes to this. I think I may have missed part of your question. Do you want to ask it one more time? Sorry.
No, just basically if you would use a model that has a 3-kilometer high-resolution domain over the US and the global lower-resolution model link domain.
Oh, you mean like blend in a global into a 3-kilometer?
No, just like you would continuously cycle, but with a global model with a very high-resolution domain. Where would this place in, just a guess?
Yeah, that's a really good question. I don't know, and it kind of depends on what is exactly our limitation here to why we are messing up our large scales in the regional model. One hypothesis is that simply you have these lateral boundaries that are just a fixed limitation because it limits the longest possible wave that you can resolve, so you're going to miss stuff. If that is the reason why we're messing up our large scales in a regional model, maybe going global fixes everything. Other reasons could be, kind of details in the DA of how we use observations and how we allow the observations to kind of spread out information around. If that's the cause of why we're messing up our larger scales, then I'm not sure high-resolution global is going to solve that issue. That's a really good question, though, and it's something that is going to have to be looked at.
Austin?
Thanks. Yeah, sorry if I missed this, but I was curious, how long did you continuously cycle for? Because isn't that part of the issue that eventually it drifts and creates its kind of own strong climatology that starts to ignore observations? Or is that more of a physics suite issue?
It's more of a physics suite issue. In this case, we cycled for 4 weeks. 4 weeks with 1-hour cycles. We did not see any bad things happening to the climate, and I'll show you that in the next part of this talk. But when we cycled, say, the NCAR Ensemble, we continuously cycled that system for almost 3 years. And we had a stable climate. Stable doesn't mean good or like representing truth, but it was stable at least.
Thanks. To basically Andreas' point, what kind of boundary conditions did you use for the forecast?
So for the forecast, the 10-member forecast, we used global ensemble. So we had perturbed boundary conditions for the forecast. Those only have an impact like once you get past 18 to 24 hours, given the size of the domain. In the DA, we used randomly perturbed boundary conditions. But again, those really just don't have much of a difference because we were so well constrained in the interior of the domain.
Craig, I have 2 questions. The first one may be stupid, so apologies. I didn't catch how do you go from 80 members to 10 members when you do the forecast. The second question is, I'm just wondering, in terms of the behavior of the cycling versus the partial, on top of looking at large versus small scale, could you tie this behavior to how the EnKF is actually maintaining the ensemble spread compared to the partial cycling, the spread you see in the partial cycling experiments?
Yeah, the first one's easier. We have 80 members. We pick members 1 to 10. It's basically the same as a random selection because all are equally likely. For the second question, we did look at the spread characteristics at 0 UTC. There were some differences, but they were relatively small in terms of like observation space spread, if I'm remembering correctly. But ask me about that again later.
Yeah, so I think we'll kind of draw this to a conclusion here so we can finish the seminar in time.
Yeah, perfect.
And then we'll have the speaker at our disposal, I guess, in the after-hour chat here. Okay.
All right, part 2. So we looked at partial and continuous cycling. We've shown that continuous cycling does at least as well as partial cycling for at least 18 hours. So now let's crank up the resolution of our assimilation system. The systems I showed before were 15-kilometer grid spacing. That's not really state of the science anymore for a regional model. We're kind of doing 15-kilometer global cycling in some places. So let's crank up the resolution and see how these convection-allowing ensemble forecasts may or may not be sensitive to the resolution of the initial conditions within a continuously cycling framework. So we already know from some previous work that when we initialize a high-resolution forecast from a corresponding high-resolution analysis, that's good, especially over the short term, where we get better forecasts than downscaling the coarse resolution analyses like we did in the first half of this talk. But when it comes to continuously cycling and high-resolution DA, most of these endeavors have been over pretty small domains. And so we want to try this over a large domain, like the entire conterminous United States, and we want to continuously cycle with an EnKF with order of 100 members. Folks had certainly done high-resolution DA over the CONUS, but previous work has been in partial cycling frameworks and typically with only 40 members. So doing continuous cycling over the full CONUS, where you have to do a new analysis basically every hour with 80 members at 3-kilometer grid spacing, it's a big computation. On its own, I think this is a pretty cool computational achievement that we were able to do. So I kind of spilled the beans. What we did is we did this 80-member continuously cycling EnKF over both this 15-kilometer domain that I previously discussed, and now this 3-kilometer domain that covers the entire conterminous United States. Ultimately, these EnKFs initialize 36-hour, 3-kilometer, 10-member ensemble forecasts of interest, kind of just like before. The experimental design here is very similar to what I just discussed for the partial cycling versus continuously cycling part. But the main difference is now is our 3-kilometer initial conditions are either downscaled or produced directly on the 3-kilometer grid. So it's this initial condition resolution that we're going to be isolating here. We did 1-hour continuous cycling over a 4-week period in spring 2017. And again, here's our domain. The first experiment is actually exactly the same as the continuously cycling EnKF I just talked about. We only did 15-kilometer data assimilation with 80 members, where we have a 15-kilometer, 80-member ensemble background that goes into the EnKF that gives us a 15-kilometer analysis ensemble that produces 15-kilometer forecasts, and then we just cycle over and over and over at 15-kilometer horizontal grid spacing every hour for 4 weeks. And then when we get to 0 UTC, we take our first 10 members from our analysis ensemble and use them to launch the 3-kilometer ensemble forecasts. And again, these 3-kilometer initial conditions are downscaled because we only have 15-kilometer analyses. In the second experiment, it's exactly the same as the first, but now we're doing 15 and 3-kilometer EnKF DA. We're putting in this 3-kilometer nest over the entire conterminous United States. So each DA cycle, we have backgrounds at both 15 and 3-kilometer horizontal grid spacing for all 80 members. These get combined with OBS into our EnKF, but now each cycle we produce both a 15-kilometer EnKF analysis and a 3-kilometer EnKF analysis. So then we get our 15 and 3-kilometer ensemble member analyses, and then when we go to run the forecast model to go to our next background, it's a 1-hour forecast, but now it's for 80 members over this nested grid. And because we're plopping in this pretty big nested grid, this experiment is at least 45 times more expensive than the first one. So hopefully it pays off because it's a big computation. So at 0 UTC, we can take 10 of our analysis members and we can use them to then launch our convection-allowing ensemble forecasts from 10 members. But now, there's no need to downscale these 3-kilometer initial conditions. We actually have 3-kilometer initial conditions. So this is the main difference compared to the first experiment that only did the 15-kilometer cycling. Our third experiment is a control. We just took NCEP's global ensemble, put them onto the WRF model grid, and press go. No regional data assimilation. So this serves as a baseline. We'd like to beat it to justify all the expense and difficulty and pain of running our own regional EnKF. So before looking at the forecasts, I'll briefly show one measure of the EnKF performance. So what's shown here on the y-axis is measure of bias and total spread. Total spread is the ensemble spread plus a contribution from an observation error. This is for radiosonde temperature observations and radiosonde zonal wind observations. The x-axis is the analysis date. So we have 4 weeks of continuous cycling in each of these panels going from left to right. The red is for the 3-kilometer EnKF. The blue is for the 15-kilometer EnKF. There's really not going to be too much of a difference between the two at these observation locations. But the key here is that after about this 2-day spin-up period, where our continuously cycling EnKF is adjusting from its initial random noise that we used to kick it off, it forgets about the initial random noise and has a pretty stable spread. We don't want to see the spread like just going up. That's bad when that happens in an EnKF. But here it's pretty stable. Same with radiosonde zonal winds after 2 days, pretty stable spread. Bias, we also want that to be stable, and we want it to be near 0. And that's more or less what we see here. So what this is suggesting is that it is possible to continuously cycle a large domain convection-allowing EnKF without any drift. This kind of gets to the question that Austin asked a little while ago. Yes, it's possible. If you have a bad physics suite, you're probably not going to be able to do this very well. And so I think a large reason for the success of being able to do this was this well-tested physics suite that we had a lot of confidence in. The other thing that helped is that we have a lot of observations over the United States, so we can really constrain these analyses. But this is, we think this is the first demonstration of being able to continuously cycle a large domain, high-resolution EnKF. And like I said, I'm pretty proud of this computational feat alone. So how about the results? This is perhaps more important. These are, again, fraction skill scores, computed just as before. Fraction skill score, again, is on the y-axis. Forecast time is on the x-axis. These are for the top 5%, top 2.5%, and top 1% of precipitation events. So if we look over the first 12 to 18 hours and just focus on this red curve, this is for the 3-kilometer EnKF initial conditions. Remember, all of these forecasts, all 3 curves, are 3-kilometer forecasts. They differ in their initial condition resolution. So when we use 3-kilometer EnKF initial conditions, we get clearly higher fraction skill scores than everything else over the first 18 to 24 hours, depending on the threshold that we are looking at, and these differences are statistically significant at the 95% level. If we look at our baseline, that's this gold color, we see it's clearly the worst. So this does justify the pain of doing the EnKF, at least for these shorter term forecasts. And then the 15-kilometer EnKF I see is kind of in the middle, this blue curve. But again, differences between the red and the blue curve, these are statistically significant and shows that there is benefit to doing this expensive high-resolution data assimilation for 12 to 24-hour precipitation forecasting over the central and eastern United States. But again, once we look after 24 hours, then we see something different. Where now our baseline experiment, when we just use the GEFS initial conditions without doing any of our own regional data assimilation, leads to clearly better forecasts than our regional EnKFs. And these differences are also statistically significant. Again, we hypothesized this was due to large scales, that the GEFS is just representing large scales better than our regional WRF-based data assimilation systems. So naturally, what we're going to do is we're going to blend again. And so the way that we did that is basically the same as what I previously discussed. We do our continuously cycling EnKF with both 15 and 3-kilometer DA, so the expensive DA system. And then we take our 15 and 3-kilometer ensemble analysis members, and that's where we apply the blending right before initializing the forecasts. So these blended initial conditions look like the 3-kilometer EnKF at relatively small scales, but they look like the global system at relatively large scales. And then given this blended set of initial conditions, then we launch forecasts. Here are the results. This is what I showed you before, and I'll go back and forth a few times, putting the blended curve on top in black. And so what we can see is over the first 12 to 18 hours or so, just comparing the black and the red curves, our blended initial conditions, shown in black, are doing just as well as our unblended initial conditions, shown in red, sometimes even a little bit better. And that's the same at all of our thresholds, where the black and the red curves are basically overlapped, or the black curve is doing a little bit better. Again, this is showing that blending is not messing up our short-term forecasts, at least for precipitation placement. There were some issues at the short term regarding spurious convection in certain places. Blending did lead to some imbalances. So there might be more elegant ways of doing this blending that could be pursued in the future. But at least in terms of where is it raining, it didn't mess things up in the first 18 hours. And then most excitingly, if we look after 24 hours, and again, look at the black curve for the blended initial conditions, we can see it clearly did much better than our unblended initial conditions shown in red. Again, comparing the red and the black curve and the red and the black curve. And sometimes our blended initial conditions even could do just as well as the cold start GFS initial conditions, like right here. The black and the gold curves are basically on top of one another. So blending is a almost cost-free way to boost your later term forecast skill without messing things up early on. We looked at other metrics that were perhaps a bit more sensitive to spread, and it's the same story. If you look at things like rock area or reliability diagrams or rank histograms, it's the same story. If I use different neighborhood length scales in the neighborhood approach, it's the same story. So I think these are pretty robust results. Before wrapping up, I just wanted to briefly mention radar data assimilation. Since we were doing 3-kilometer DA, arguably we should have been assimilating radar observations, but we weren't in the experiments that I just discussed. But we did run another experiment where we did do some radar data assimilation, where for a 6-hour period before our 0 UTC initializations, we assimilated radar observations over the entire CONUS and just reflectivity observations. So sometimes we assimilated 200,000 radar observations at a given time. This actually can occur very quickly in the DA system because we only allow those radar observations to impact a small area. So here's the impact. And it's not very exciting beyond the first couple of hours. Fraction skill scores on the y-axis, forecast time on the x-axis for the top 5, 2.5 and 1% of events, 3-kilometer EnKF initial conditions in both of these, red without radar, same experiment I just discussed, and then the blue is when we threw in the radar. So at the very start of the forecast, the first 3 hours really, you can see some difference where simulating radar reflectivity observations was helpful. And these differences were statistically significant. But thereafter, you're really hard-pressed to see any benefit of radar observations. And these findings, I wouldn't say they're too different from what's been put out there. Folks who really are into radar DA, they might argue a little bit with it and say, oh no, we can get benefits further out. But I think those are kind of few and far between to really see the benefits of radar observations beyond 6 hours or so. So that's basically it for part 2. I'll just summarize these takeaways. So yeah, it is possible to successfully continuously cycle a convection-allowing EnKF over a large area. You can do it. Short-term EnKF initialized forecasts were better than the corresponding GFS initialized forecasts, so there is justification, at least for short-term forecasts, of doing this expensive EnKF data assimilation. Benefits of 3-kilometer data assimilation compared to 15-kilometer DA through about 12 hours. Thereafter, the 15-kilometer assimilation experiment did just about as well as the 3-kilometer DA experiment. I didn't really talk about that very much. But blending, again, it kind of gives the best of both worlds. And it's basically cost-free. We get the benefit of high-resolution initial conditions early, and then we get a performance boost later. And so I really think blending is an interesting way, an interesting possibility to unify kind of nowcasting systems and next-day forecast systems. So for those of you familiar with the Warn-on forecast system, that's basically a nowcasting system. And then you have the current models that are being run out to 36 or 60 hours. I think there's really nothing besides imagination to kind of combine those two into one system. And I think that blending really could be a way forward. Again, all the gory details, and there are many of them, they're in a paper in Weather and Forecasting. And that is all I have, so thanks for listening.
The floor is open.
Great talk, Craig. When you talk about using radar data, and assimilating radar data, it seems like there's a lot of ways that could be done. I mean, for example, if you just put in reflectivity without adjusting other fields, then you can have problems because things are unbalanced. So how did you do it for this particular experiment?
So the EnKF is nice in the sense that given a radar observation through covariance structures, it updates other things as well. So you at least have a consistent, update through your ensemble. That doesn't mean it's like a perfect update. The covariances are noisy and stuff like that. But that's how we did it. It's just a pure EnKF data assimilation. No other bells and whistles or tricks. No latent heat calculations or anything like that. Just a pure EnKF technique.
So we have a couple of questions from the Slido audience. is from Judith Berner. Would you get the same qualitative results if you looked at the dynamical variables, for example, U or T?
Good question, Judith. I didn't spend a lot of time looking at it. I don't know. In previous work where I have looked at those, it's kind of harder to see differences in those dynamical variables across experiments, these types of experiments. That's a good question.
And another one from Falco is, do you think it's correct to assume that the difference between the 3-kilometer IC and the 15-kilometer versus the GFS IC gets larger beyond 36-hour, making blending even more powerful? Also, I'd argue that your results motivate global convection-allowing DA.
I agree. I also think they motivate global convection-allowing DA. I'm kind of hesitant to speculate on this. I mean, I don't know. I could argue it either way.
Completely different question. How close were you with your experiments running that in real time? In other words, the computational power you threw at it, would you be able to squeeze that into an operational cycle and complete all this within the time?
Yeah, I think it was something like, given at least on Cheyenne's supercomputer, I think we can do this in real time with like 25,000 processors. This is totally doable in real time. I mean, and for instance, like the HER ensemble that folks across town have been running for years, they do DA over the full CONUS at 3-kilometer grid spacing. They only have 36 members in their ensemble, in their EnKF, but they can do it. So yeah, I mean, a system like this is totally doable in real time, given modern computing. We can keep up even hourly cycles.
Okay, we have one here. Thank you for your nice talk. How does blending affect boundary conditions?
The blending will impact the boundary conditions. You'll be forcing some areas along the boundary to look like large scales. We kind of do account for this in like an updating step right before we run the forecasts. But we didn't look like at a sensitivity study to see how this is going to specifically impact the boundary conditions and how that might impact the forecasts.
You mentioned some artifacts from blending. Would you say a little bit more about what those were?
Light precipitation in areas where you might not expect light precipitation. That was about it.
Lasting for?
Transient, an hour, 2 hours.
Okay.
So that 15-kilometer simulation, was that also convection allowing, or did you have parameterization turned on?
So in the 15-kilometer data assimilation system, we used a convection parameterization scheme. Then when we downscale to run the 3-kilometer forecast, there's no cumulus scheme. But the 15-kilometer DA system itself certainly had cumulus parameterization.
I think we can cut it off now. It's 3 o'clock, and we can carry on discussion in the by the coffee pot. Thanks again, Craig.